Alrighty, recording is happening. So here we go. Let's see, what do we got on? So we got some geo news. I just want to remind everybody that the November 6th class is going to be asynchronous with basically I'll be giving you your final project instructions for you guys creating your own Google Earth tour creation, virtual tour creation. So you'll have another chance to play around with a simple one that I made today to give you a few ideas. But I think the idea here is, basically, who knows what's going to be happening during that time. So try to plan accordingly and, just make it as easy access for everybody. So that's the goal for November 6th. All right, so then today we'll be talking about the processes of rock and weathering and soil. We'll do a breakout using a texture triangle for soils. We'll take a quick little break. We'll do a mass movement virtual tour, which I expect will maybe take 25 minutes, maybe a half hour or something like that, where you guys can look at it and we'll have a discussion of how you want to try to do this, depending what the internet is like. And then a few little mass movement descriptions, kind of tying everything together that you've observed, and we'll go from there. So the geo news for you to geo knows, I don't know if you all saw, oops, sorry. I don't know if you all saw this last Wednesday. Yeah, today's Friday. So on Wednesday, this past Wednesday, basically what happened is we had this OSIRIS-REx, which is a cool little space probe that was launched back in 2018. And it was orbiting Bennu, which is a small little asteroid in somewhat of a somewhat similar orbit to Earth. It's a little bit outside of Earth's orbit. But basically, NASA sent a lander, was able to orbit Bennu, which you can see in the bottom right-hand corner there is about the same size, a little bit taller than the Eiffel Tower. It's a really small object, but if you remember from the very first or second week of class, we talked about that solar nebula of all the chunks of rocks and stuff in space that kind of glom together to become the Earth. This is one of the leftover bits. And so scientists want to know, why is it left over and what's it made out of? So they landed this probe onto that asteroid, got some samples and kind of sprung themselves back up. And what's going to happen is in March, they're going to fly this spaceship back to Earth and try to understand what this Bennu is actually made out of and see what's inside the rocks that it's going to bring back, which is pretty cool. So by, let's see here, 2023, it'll be landing in the Utah desert, and we'll be able to see some really amazing asteroid rocks brought back to Earth. Japan did something similar 2 years ago, and their probe will be landing back on Earth within the year. And so we'll keep our eyes out on that. So I thought that was pretty cool. The other big news is really bad extended fire weather hazard risks coming up this weekend, especially Sunday into Monday. Monday's going to be very windy here. And not only is it going to be very windy, but it's going to be super dry air. So like 5% relative humidity, which means very, 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 very dry. And at those relative humidities, the moisture actually sucks out of the plants and into the atmosphere, which dries them out even more. So all the plants that are in California, we've had a drought, they're super dry, add a dry air mass, and now up in the Sierras, they're looking at maybe 60-mile-an-hour winds, and down in the valley here, 20 to 25-mile-an-hour winds with gusts up to 45 miles an hour. So it's going to be an interesting Sunday, Monday, and very bad fire weather, basically, is what we want to say about that. So just be vigilant. If you do go out this weekend, don't do anything to make a fire. And here is one of the tools we'll be looking at. Hopefully it'll load, we'll see here. But this is earth.nullschool.net. And this is a computer model of Sunday and Monday showing the atmospheric winds at, this is the atmospheric winds next Monday or so, but it also shows you how fast they're traveling. So if you click on here, up 120, let's see what we've got here. About 76 miles an hour up about where the airplanes fly. So that's pretty strong. And some of those winds will be dropping down into California, but you can see we have this counterclockwise circulation out here. We'll be learning in the next few weeks. This is what we call a high pressure system. And we have a low pressure system out to our east, which is counterclockwise. And if you've been following the news and the weather, all of this wind and air from the cold north is diving down into the Midwest right now, and they're starting to get some snow, which is interesting because it doesn't feel like that at all in California, although it will be down into the low 70s here by the end of the week. So that's some of the geo news you needs to geo knows. I think I had one more. I can't remember. I don't think so. Nope. Okay, that's it. So that's the geo news you need to geo knows. Just be aware of that. Oh, we had an earthquake in Alaska. I forgot to put this on here on Wednesday night, I think it was, and it created a small little tsunami. It was a strike slip, but it had just a little bit of an upward motion to it. So it created about a 1.5 foot tall tsunami in Alaska, and it created about a 5-inch tsunami off the coast of California. So it wasn't big or devastating or anything like that, but it was a magnitude 7.6 earthquake in Alaska, mostly strike slip. So kind of like the San Andreas fault. So I thought that was kind of interesting if any of you happen to see that in the news. So far this year, we've talked about the igneous rocks and the metamorphic rocks and the internal earth processes that have created them, right? So we talked about subduction and melting and all that good stuff. Well, now we've also seen how mountains are built and plates colliding, things like that, volcanoes being built taller. Those are all driven by Earth's internal heat and processes. So now we're going to start looking at some of the external processes of the Earth and how that affects the rocks and breaks them down. So these are things driven by solar power, the sun, heat, weather, rain, atmospheric patterns, things like that, and how they affect rocks for right now. So for this week, for your sketch notes, here's what we're looking at. For the big idea, like number 9, how can weathering and erosion of rock be both beneficial and hazardous for life? That's what we're going to try to tie together everything in the context, the lens of tonight. So basically, we're going to spend the first part of the night looking at mechanical weathering and chemical weathering, figuring out what does that mean to have these rocks weather, give you a few examples. We'll take a look at the soil that it makes, and then we'll take a look at mass movements. So when we talk about mass movements, that's our landslides, and there's like 5 different flavors of those down there that you can see. Oops, hold on, sorry. I meant to admit somebody into the class and I missed my marker. So give me 1 second here. There we go. Oh, they're coming. All right. So when we talk about mechanical weathering, basically this is what happens to rocks when physical forces break them into smaller pieces. So mechanical weathering means you're taking a rock, you're smashing it, you're breaking it, it falls, it disintegrates. Something is breaking it into smaller pieces through a physical interaction. Maybe you're smashing it or driving over the top of it. Something physical is happening to it. So water movement, ice going atop of it, or breaking it, or wind or temperature variation. So you take a big rock, make it into small pieces, bam, piece of cake. So basically, if this was our lab class, we would kind of take some time to experiment and play with some of these ideas. But here's what you need to know. You can take a block, and I don't know if you've ever used like sugar cubes for coffee or tea or anything like that, but if you put a whole entire sugar cube in a glass of warm water and you put the same amount of sugar that was just granulated and not in a cube, the stuff that's not in a cube is going to dissolve much more quickly. Oop, let's see here, chat. Can't see the bottom of the slide. Oh, okay, well, let's see here. Basically all it says is, let me see. Let's try that. That's interesting. Yeah. There's only 2 things on there. So it just says the more surface area equals faster weathering, Kelly, if you can see that. So it says, sorry, but the reason why a bunch of sugar will dissolve faster, and the reason rocks will break down faster if they're smaller, is it has more surface area to it. So if you think about this big square, the 16 square units, if I were to cut that in half a couple of times, so 1, 2, 3 times, and make these smaller pieces, I'd be exposing a lot more surface area that allows water or wind or other things to attack it and break it down. So once you get a big solid rock starting to break into smaller pieces, it gets smaller and smaller and smaller much more quickly than just a big piece. And that's what I just want to kind of mention here, is that Smaller pieces have larger surface area. And so when you have more surface area, that creates faster weathering because there's just more surface to attack. So let me show you a couple different types of mechanical weathering. There's 4 types. So one that's called frost wedging. There's one called unloading. There's one called biological activity, and then salt crystal formation that can cause this mechanical weathering. And I'll give you some really cool examples here right now. Oops, I forgot that one was there. So with frost wedging, the mechanical weathering type of weathering called frost wedging, if you've ever left a soda in your fridge or your freezer by accident, you know, and you come back 3 days later and you forgot about it, but inside of your freezer is covered in soda pop that's exploded everywhere, kind of like my picture is hiding right here. Water expands when it freezes. So if you get some water that goes into a crack in the rock and it freezes at night and expands like up in the high mountains, that can put stresses on the rocks and cause them to break. And if it happens over and over and over again, that frost wedging, it's kind of like a paper clip where you break it too far, you make it very weak by rubbing it back and forth really fast. So that's one way. It's called frost wedging. And in real life, this is what it kind of looks like up in the Sierras and the granites. Up in the high mountains where it freezes a lot, you'll definitely find rocks with these kind of cool big giant cracks in it. And that's from frost wedging, where in the daytime it gets warm enough where water will melt, or maybe you get a rainstorm in the fall, and then at nighttime the rain starts freezing in those cracks. And as it freezes, it expands, and it's like a hydraulic jack and just starts breaking them apart. So that's frost wedging. The next type is called unloading. And so unloading basically occurs from, if you have rocks that were formed deep in the ground, like the big plutons of granite that we learned about, remember those are the blobs of melted subducted plate that start coming up to the surface. Those cool off and crystallize 4, 5, 6 miles underneath the earth, buried underneath 5 or 6 miles of sediment and rock on top. And if that 5 or 6 miles of rock on top eventually gets eroded away, then you have exposed mountains like the Sierras, like we see here, but there's not as much pressure on them anymore. So it's kind of like if you were wearing a backpack to school, and it's really heavy, and all of a sudden you took your backpack off. It's like, you kind of relax and expand and can stand up a little bit straighter. The same thing happens with these rocks, is the crystals in those minerals want to expand, and they kind of start popping. So these rocks expand as the surrounding rocks, the surrounding weight of the rocks are taken off. Excuse me. So let me just show you, I just explained it, but let me show you. There's no video on this part, so don't worry if you're not hearing anything. This is kind of how the Sierra Nevada formed. Sorry, there's lots of loud traffic out front. But this is kind of how the Sierra Nevada formed. We had our subduction, and as the crust starts subducting, then you get the melting, which then pushed up and made the volcanoes. So where the Sierras are now, 100 million years ago, there were volcanoes. And then about 60 million years ago, most of those started cooling off, making the plutons. Erosion happened for the next 50, 60 million years or so. And those softer sediments eroded away. A lot of them flowed down into what would then become the Central Valley. And basically what we have now are the granites that exposed. And so now, because we have the granite that's exposed there, sorry. It started out deep, but now it's exposed, and there's less weight on top, and you still have the rocks on the side kind of pushing it. And I wish I had some bread. I don't have a slice of bread, not because I'm hungry, but if you were to kind of push that side of the bread together, a slice of bread, it would kind of arch and pop up, just like you see the granite doing here. And so this is what we call unloading. That force, as the rocks try to expand and pop, will break off and do something called sheeting and exfoliation. So you're taking the load off the rocks, and then they start breaking like this. And this happened very near in Twain Harte, so it's just a little bit up the road from Sonora. My cabin is literally a half a mile from this spot, and about 5 years ago, some exfoliation happened in person. And I just want to show you what that looks like. So I will turn on the sound here. Got to share my sound, so give me a sec here. Oh. All the way down. This whole seam now is active again.
Lots of activity down below. It's still lifting.
You can see those little cracks starting to pop up there.
Did you see that? Just popped right up.
I felt that one.
Little piece flew into the air.
Then a big piece flew into the air.
Yeah, baby. Now maybe you'll be happy.
So that's the first time that we know of an exfoliation like this was ever caught on film. That was a few years ago, and there just happens to be a small dam there making a lake. And it was a worrisome time for a bit, thinking that the dam might actually break and flood everything down underneath. It's a small lake, but it still would have done a lot of damage. So you can see that rock just kind of expanding, popped, and then it settled back down after everything broke. But now the next time the rains come or you get a flood or something through there, it can wash that upper layer of rock off, which then will break it down into other pieces. Oops, sorry. So if you have ever been to Yosemite or up into the granites or Tahoe or any place like that, it's usually the granite rocks, the granitic rocks that really show this exfoliation, what we call sheeting as well. It just looks like these little layers of an onion peel popping off, and they slide off from time and time again. And you can see the big piles of rock down here at the bottom. And by the way, I just want to mention this. Yosemite National Park, you have been needing a reservation to go, but at the beginning of November, November 1st, you can start going into the park, just paying the regular entrance fee without a reservation now. So if you want to go see some of these things on your own, it'll be much easier to do that in terms of you don't have to have a permit. I mean, you have to have a permit, just no reservation. So you can just pay. It's like $20 to get in, or $30, I think, but it's good for 7 days. And here is some sheeting and exfoliation where you have rivers going across them up in the Sierras by Tahoe. So, and then if you've ever hiked Half Dome, this is an old picture of me from like 2002 or something like that when we did Half Dome, but you can really see Half Dome is a great example of this sheeting and exfoliation, and that's where it makes the dome shapes. So that's what you're seeing right there, is all that exfoliation. And eventually some of those slabs, they'll fall right off, and just hope you're not there when it happens. So we've got another one then, which is called mechanical or biomechanical weathering. And so this is where tree roots or animals, either the roots will grow and break rocks apart, or you have burrowing animals that dig holes and move dirt and things around like that and break rocks as they move them around. So that's called biomechanical. Living things are breaking the rocks. You can see that in this case, there's roots growing into the side of some granite there on the side of the road. And eventually those roots will get big and start breaking up the rocks. And here's a cool rock in Oregon that just grows on the side of the rock with its giant taproot. But let me show you this really fast. Maybe, I hope it'll load. It looks like my internet speeds are catching back up. Maybe not. Yeah, we're all right. All right, so this is a 3D model. It's an actual tree root in granite up near one of my favorite places by Sonora Pass. And I just took a whole bunch of pictures and made it into a 3D model. But what you can see here, I didn't quite get all the pictures there, but you can see the roots growing into the rocks and how it split the granite apart. And it started out as a teeny tiny root, but as the root grew, it just split everything and will break the rocks down. So that's biomechanical weathering. And the link is on this presentation here. If you want it to go play, you can download that and play around with it as well at some point. So another one is called, the last one of mechanical weathering here is called salt crystallization. And guess where salt crystallization happens a lot, where it happens very frequently. Anybody want to take a guess where there's an area where there's lots of salt all the time?
In the ocean?
Yeah, near the ocean, near the beach. You got it. All right. So basically the salt water will spray onto the rocks, and then as the water evaporates, salt crystals will form. And it's kind of like frost wedging, where water gets in a crack and expands. Well, if salt water gets in a crack and the water evaporates and the crystals grow over time, it can cause this funny looking rock called tuffone and get erosion happening like that. So that's another way of mechanically weathering it. So there's no chemical interaction. It's just the salt crystals growing that pop out other pieces of sediment and things. So it's pretty cool. Ooh, all right. So those are the mechanical ways of breaking it. There's also some chemistry ways of breaking it. And I hope once this pandemic is over, you'll all get a chance to go to some of the caverns that are in the foothills. Basically, the caverns that are there are made out of a type of rock called limestone, calcium carbonate. And it's, if you've ever done vinegar and baking soda experiments where you've poured vinegar on top of the baking soda and it fizzes and dissolves the baking soda, the same thing happens here. Where the rain, when rain falls through the atmosphere, it picks up a little bit of carbon dioxide from the atmosphere that naturally exists, and it can make it acidic. It's called carbonic acid. So it makes the rainwater slightly acidic with carbonic acids. It's the same thing that makes your sodas fizz, but your sodas are, thousands of times more acidic than rainwater. But over time, over thousands of years, the carbon dioxide can dissolve, it dissolves in the water, and then when it goes into this carbonate bedrock like limestone or marble or things like that, it has a reaction, and that carbonic reaction or carbonic acid dissolves away the limestone, and over time will create these big caverns underneath, which is pretty cool. We took my wife there for Mother's Day a few years ago. It's pretty awesome. So in nature, like I said, over thousands of years, those large quantities of limestone are dissolved and carried away by groundwater moving underneath them. And we'll talk about groundwater later on, but it's kind of rare to have like underground rivers totally moving through. But in some of these cases, there literally were underground rivers in these caverns moving away the dissolving bits of the cave there. So basically, if you live in the South or the Midwest or the Southeast and you have lots of limestone areas, I should mention the limestone is the remnants of old tropical reefs. So it used to be a tropical reef environment 300 million years ago, but now it's just limestone that everybody builds their houses on. If you don't choose well, there might be a cavern underneath your house that continues to dissolve. And all of a sudden, one day, the roof of the cavern collapses under the weight of your house and everything falls in. It's called a sinkhole. And in Bowling Green, Kentucky, a couple of years ago, it happened underneath the Corvette Museum. They have a big Corvette museum there, and like several $100 million worth of Corvettes and cars went right into the sinkhole in there. So anyways, chemical weathering can be damaging for sure. And it can also be beautiful. In Mexico, down like near Tulum in the Yucatan, a lot of carbonate rocks that have been dissolved to make caves back in the day when sea level was lower. And so it was able to dissolve the caves. And now as sea level has risen over the last several thousand years, not during the ice ages, it fills up these big caverns and it makes cenotes, which if you've ever been to Mexico, these are not my pictures, but if you've ever been to Mexico, lots of folks like going to the cenotes, and it's basically cave diving in these beautiful clear waters, which are pretty cool. And all those caves were formed from the limestone being dissolved. And then there's also chemical weathering happened at Mammoth Caves, which is also in Kentucky. Ooh, somebody did cenotes when they went to Cancun. That's awesome. So a couple of years ago, 2 years ago, I went to Kentucky for a conference, and I was able to get a national parks permit to go in and make these really super high resolution photospheres. But check this out. So basically, these caverns were actually used by people, but you can go in here and there's a link that if you would like to, you can go into these rooms and check them out for yourselves. Let me get to the good one here. And, pre-Civil War, so let me just put some context. These caves had been used by humans for over 4,000 years. There was a Native American population that used them for 2,000 years, and then usage stopped, and then they were kind of rediscovered in the 1700s and 1800s. But you can go around and you can take a look at all these cool things like, oh, when I say high resolution, it's super high resolution. Give it a second to download. And you can take a look at, this is an old ladder, a 4,000-year-old ladder that the Native Americans used to get from ledge to ledge up in these caverns. So you can take a look at all these really cool places. I'm hoping to make some of these for our local areas as well too. But this is all dissolved. Kind of crazy, right? Water doing dissolving. It's hard to believe sometimes. Oh, I want to know why it's called the tuberculosis room. Good question. Oh, gosh darn it. Sorry. Let me get back to that. So it's called the tuberculosis room because back in the early 1800s, it was thought that tuberculosis could be cured if you put people in a dark, dry environment or humidity controlled, temperature controlled environment. So this stone building that you see here was part of a tuberculosis hospital in the early 1800s where somebody tried to heal tuberculosis patients because they didn't know how to heal them at the time. That doctor ended up getting tuberculosis and dying as well. And after the tuberculosis hospital was dead and gone, it turned into a hotel and a few other things. So, you know, pretty crazy, right? And you can see all these graffitis that are here from the early 1800s as well. Just kind of cool. So anyways, that's a good question. But you can go check it out on your own and see. So this chemical weathering here, I want to mention this. So there's my son standing on some really cool granite rocks over by Beardsley Lake off of Highway 108. But I don't know why the resolution of this picture came out so bad. But here's what you need to know. Granite can chemically weather. And the feldspar minerals that are in granite, that one mineral called feldspar that's along with the quartz and along with the mica that's in granite, when it weathers, what you need to know is not necessarily this huge chemical equation, but what you need to know is that potassium feldspar turns into clay, and then it also has potassium ions and stuff in it as well, and little bits and pieces of silica. So granite weathering is very important to the valley. It's part of the clay and the soil that we use here, and it produces the silica that we use in our soils as well, which is the sand. And it has potassium ions, which if you know grow plants, you need potassium for the plants to grow properly here. So the breaking down of granite actually is what we farm on here in the Central Valley, the broken down remnants of the granite, which is pretty crazy to think about, right? So another way you can tell about chemical weathering is oxidation and rusting. And basically you can kind of ignore the chemistry part here, but if you have minerals that are exposed, that have iron in them, that are exposed to the oxygen in the air and the environment, they will rust over time and oxidize, and that changes its chemical composition and will break it down. And it also turns the rocks orange and red. So anytime you see orange and red rocks, you go, oh, there's iron in those rocks there. All right. I just want to show you a quick little thing of one of the forms that chemical weathering can do on rocks, and it's basically called spheroidal weathering because, hey, guess what? It takes regular rocks and it breaks them down and makes them look like spheres. So it's basically rocks become rounded over time because the edges are chemically attacked, like we talked about earlier. And over time, they can get these rounded edges to them, which is pretty cool. And sometimes they just break off right in half, and you can peel off these little flakes, and it looks like exfoliation, but it's not exfoliation here. This is literally spheroidal weathering, where there's chemical processes eating away at the rock here and not physical processes that are trying to break it up. So that's pretty cool. And then if you've ever been to Joshua Tree National Park, all of the granite rocks that are down in Joshua Tree are all spheroidally weathering, which is pretty cool to go see. I highly recommend it in a not pandemic. All right, so a couple of last little things here. In terms of weathering, the rates of weathering, so we have the the mechanical weathering, we have the chemical weathering, but two factors really influence how fast that happens, all right? And the first one is the rock characteristics, like how strong is the rock? And so granite on this side over here on the left is really strong. The carbonate rocks are susceptible to chemical weathering, so it dissolves and goes away. So if you're into headstones for yourself planning in the future, you always want one out of granite and not marble, because marble will basically just be in 100 years washed away and you won't be able to read anything on it. But so the stronger the rock, the harder it is for it to break down. And also climate. If you have a warmer climate, you're going to have faster weathering. And if you have cold climates, you're going to have kind of slower weathering. So weathering doesn't happen as much in cold climates as it does in warmer and especially moister climates. There's another type of weather, or not a type, but another explanation of weathering here, which is called differential weathering. And so sometimes you have rocks that have different strengths within them, and some of them will erode faster than the others. And if you go to places like Bryce Canyon National Park, where you see right here, that was a weaker layer of sediment than the rock on top. So it erodes away first, and it leaves these cool spires called hoodoos. And it's usually due to different mineral differences and the spacing and cracks that are in those rocks. So you can get hoodoos, or if you go to Utah, you can see these goblins at the Goblin Valley State Park, which the stuff underneath it is really muddy. And then the stuff atop of it is like a harder sandstone that doesn't want to dissolve as much. And you can see on the right here, there used to be a goblin standing up on this spire, but it dissolved so much that the rock on top just squashed it. So that's called differential weathering, where the stuff underneath weathers faster than the stuff on the top. All right, so it's more resistant to erosion, and this one is less resistant to erosion. And all of these are like 10, 12 feet tall. And there's a dude in the news like 10 years ago that was with his Boy Scout troops and thought it would be cool to push a rock at these preserve parks off. And he ended up getting arrested because he videotaped it. So, oh well. And here's those hoodoos in Bryce Canyon National Park. If you've never been to Bryce Canyon, but you have been to Disneyland and you've been on the Roaring Railroad in Disneyland, it's all modeled off of Bryce Canyon here with the hoodoos and the differential weathering. And you can see off in the distance over time, given enough time, it'll all just erode down into the kind of these soft, gentle hills. So that's the fate of all these hoodoos. Eventually, they're all going to erode down to pretty much nothing, which is kind of sad. All right, I think we're doing good. We're doing good. So I know we're sitting tight and listening here. I promise our first activity is coming up, and then towards the end, you have a lot of time, of group time and work. So I just want to kind of set the stage here, and I appreciate you letting me go through some of this. So here's a funny little 1 minute inner, well, you'll see, a break.
Can you imagine a world without dirt? It seems like dirt is everywhere. Chances are there's dirt somewhere underneath you right now. Many things grow in dirt, like carrots. Carrots are good to eat, but you should never eat dirt. It doesn't taste very good, and you might get dirt. Dirt is dirty, so if it gets on you, wash it off right away. Rocks are dirty because they're found in the dirt, and they have dirt on them. Some people like to study rocks. Whatever. But where does dirt come from? Scientists have been trying to answer this question for thousands of years. Most researchers now believe that dirt is actually nothing more than dried up mud. When mud dries up, it becomes dirt. And when dirt gets wet, it becomes mud again. So which came first, dirt or mud? You might as well ask which came first, water or ice cubes. It remains one of the mysteries of the universe.
So, thanks for indulging me. Soil is kind of a dirty subject, and that's what we're going to be talking about. There's lots of dirt here in our Central Valley. So what makes dirt soil? And obviously that was a tongue-in-cheek joke. I hope you guys understood that. I mean, you knew it was a joke when they said they study rocks, whatever. I mean, that's just a slap in the face. So we're going to try to take then, we just showed you how to break those rocks down. When those rocks get broken down in the mountains around us, they flow out to the Central Valley and deposit, and that's where we get the sediments that we need to have all the agriculture that we have in the Central Valley. So I think that's kind of a big deal to know, especially for those of you that are going to be teaching here. You know, when you start looking at science lessons to do, the way we are connected to other places is really overlooked a lot of times. So hopefully we can figure out how this happened. So our Central Valley got its start with mineral sediments that were weathered and eroded out of the Sierras. And the stuff that we actually farm on, the soils we actually farm on, and you can see all the just patchwork of farmlands out here. Most of that soil, the most recent stuff on top, was brought out from glaciers during the last ice age about 12,000 years ago. Yosemite kind of looked like this. So here's Yosemite Valley. Here's the Grand Canyon of the Tuolumne River. There's a huge ice sheet in the Sierras in the watersheds that we live next to. And if you've ever seen rivers in the Himalayas today, those glacial fed rivers are really big and really huge, and they bring out lots of sediment that get washed out with it. And so up until about 12,000 years ago, that's what was happening in the valley, where these big, huge glacial outwash rivers, so the Tuolumne and the Merced and the San Joaquin and all those were just completely much bigger rivers back in the day, and deposited lots and lots of soil, or sediments, I should say, from that outwash, which is now the soil that we farm on. Basically, I'm going to skip that one because that doesn't really make sense for us. So here's the deal. One of the things I'm asking you to do in your sketch notes too is what are the 4 components of soil? Let me just ask you this, and if you've looked at the notes ahead of time, don't tell anybody, but what is soil made out of? Can you guys think of anything? We live in the valley, but I just like to hear your ideas. What's soil made out of?
Minerals?
Minerals, a great one. All right. So minerals is a good one. What's another thing that's in soil? Let's think here. You can chat it. You can say it. There's no wrong. I'm not docking if you say a wrong answer. So I just want to hear ideas.
Dirt?
All right. So dirt is kind of a synonym for soil. And it's also has the mineral parts in it. So the minerals are the dirt part of it. All right. Let's see. I got some more chat folks coming in. Nutrients. Ooh, worms. Oh, worms. So like living things. And sand would be kind of the minerals. Nutrients definitely would also be part of the minerals for the most part, some of it. So how about this? If I were to give you a jar of dirt, basically only half of that jar is actually mineral matter. The rest of it is air. So there's lots of air in between those spaces, and there's lots of water, depending on, that can change, if you just watered it or if it hasn't been watered in a long time. And then there is a little bit, for the folks that said worms, there's a little bit of organic stuff in there, organic matter that then can become nutrients, either from the soil minerals or from the decaying organic matter that's in there. So that's what soil is made out of. And a lot of folks kind of forget. They just say, oh, it's all minerals. Well, if you just had all minerals, you're not going to be growing much, because that's what Mars has. That's what the moon has. It's just straight up minerals. And if you ever watched The Martian, you saw how he had to get potatoes to grow, right? He had to add a secret ingredient. So how would soil look with no air? That's a great question. That would then just be a rock. So imagine like sandstone. If you took sand or silt or something like that and you compressed it, then it would just be sandstone or mudstone or something like that. A sedimentary rock is what that would become. So that's a good question. So in the soils, then, we have these different textures. So especially if you come from a farming background, you may or may not in the Central Valley, there's probably a likelihood that you know somebody that farms or know a farmer maybe. And if not, that's totally okay. But basically, the way we classify soil is through what we call a soil texture. And it basically is the proportions or the amount of clay, silt, and sand that are in the soil here. And so down at the very bottom, if I can let that silly thing go away, the clay is the finest grain mineral stuff. It's like really, 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 really fine powder grain. And then it goes up to silt and then to the different types of sand that are up in there. And so what we have on the right-hand side here is this texture triangle. And normally in this class tonight, we'd be bringing in some soil samples and we'd be playing with them and trying to figure the stuff out on our own. But this is gonna be our first breakout here, where you guys are going to try to determine the texture of some random soil sample percentages of how to use this triangle. And then you have one little bit of homework for this week, and it's super simple. You just got to go out to your outside, find some place that has a little bit of dirt, and then try to classify what the soil is. It's really simple, I promise you, and it won't take long. It's not a burdensome thing. It's more supposed to be a fun thing. So let me get my my soil texture jam board here. There we go. everyone. All right. I better look. Is somebody in the waiting room? No. Okay. So there's the Jamboard. So I'm going to break you out in just a few moments here. And what we're going to do. Oh, no. Did I bring my.
I don't have access to it.
Oh, man. Okay. Here. Let me share it. I forgot to do the right share. I'm sorry. Oh, come on. Just a minor oversight here. There we go. All right, I think that should work now. Oh yeah, people are in, okay. So let me show you how this works. I'm gonna share my screen here, and I got a new digital tablet toy, so I'm gonna try to drag this over and share a different little portion of my screen. Oh, come on, if I can find my, hello. Well, I've just lost my Zoom window. There it is. All right. Sorry. It disappeared on me. Share screen number 2. All right. Are you guys seeing a blank screen over there? I hope so. I'm going to drag this over. And now I think you'll be able to see my fancy dancy screen over here. I'm going to make it bigger. So this is our soil texture triangle. And let me know if this, just chime in and say something if you can't see this or it isn't working. But I'm going to use a little highlighter here. I hope you can see the little yellow dot. So what you're looking at here is this texture triangle. And on one side, it says % silt. So if we have, it goes from 0 all the way to 100% silt. On the bottom, we have the % sand, which runs kind of this direction. And then the % clay is on the left-hand side of this triangle. And so if you want to try to classify what type of soil you have, and the reason we're doing this and the reason why it's important to classify the sands or the soils is it helps us know what we can grow on those different soils. And I'll get back to that in just a moment. But basically, what you're going to be looking at here, I'll do number 1 for everybody, but the idea here is we want to try to put a number 1 through 6 on what type of soil each one of these samples are. So for number 1, it says it has 20% silt. We took some soil, we ran it either through a sieve or we put it through, like we washed it a little bit and we separated all the different types of minerals out, the sand, silt, and clay, and we can figure out percentages. So in order to figure out the name of this type of soil, that's what the texture triangle does. And it's what I should have said earlier is that this tells us the name of the soil types. You start out with, in this case, silt. So my silt is over on my left-hand side. Here's my silt over here. And it says 20%. So here's 20%. And if you notice, the numbers here are angled along the same direction of these lines. So anywhere along there is going to be 20% silt. Okay. So I have that part done. And then I want 10% clay. So my clay side is over here. So notice my clays, here's 10% clay. I'm going to just kind of draw a line that goes over that way. So I've got my 10% clay, and then at 70% sand, here's my sand down here. Here's my 70%. You notice the numbers are tilted up right here, and I intersect it right there. So where all those intersect, I'm going to go down and put the number 1 for the number 1 of my soil. And then I'm going to take the eraser tool right over there. And I'm just going to erase those other lines. And so for number 1 right here, the name of this soil type is sandy loam. It falls into this, oops, let me see here. It falls into this little box right in here. So anything in those lines are going to be called sandy loam. So I'm going to put you in a breakout group. This should take like 7 or 8 minutes. And what I would like you guys to do is try to collaborate and figure out, all right, if I have 30% sand, 10% clay, and 60% silt, what is the type of soil name that I have? All right, and then we'll figure out why that's important in just a moment. So Are there any questions so far? I know this one might be a little confusing, but does it make a little bit of sense of how this works?
Yeah, it makes sense.
Okay, cool. So I am going to then put you all in breakout rooms. You don't have to do number one. Well, everybody can look at mine and copy number one if they need to do number one, and then find your breakout group number and see what's happening. All right. Oops, I got to get my thing back. All right. Breakout rooms. Assign automatically. Let's see here. All right. Assign automatically. Here we go. Have fun. See you on the other side.
And then 10% clay. So now I'm gonna draw a line. Oops, if I can go, or let me draw one with the pen.
And then point that.
30% goes up, and then 10% clay goes like that. Oops, sorry, it's not the straightest line ever. 60 goes down like that. So they meet right here, right?
So
it's
wait.
silt alone.
So I have a question. So clay is always like you just go all the way across. Okay, I get it now. I get it. You just always go across from the percent, like
yeah,
make
follow
that.
the line.
Okay.
So let me just.
Everybody, good job. I was just joining in to see, but continue on. Excellent.
Okay, so 30%, 10%. Oh,
maybe like a
I did black
black.
because it doesn't have like the background. Oh wait, hold up. Maybe no, I don't think that's the background for that one.
I think
Yeah, no,
as
it's
long
not.
as he can read it, it's fine.
Yeah.
Yeah,
Hi guys.
yeah.
It's fine. Just drag it in there anywhere. Don't worry about too much readability. It's just kind of like going through and figuring out where it is. So
Okay, alrighty. Because we were kind of confused. We're like, how is he gonna see this? We can't even see it.
well, that's totally fine. Or you can just take and drag the number with the arrow or something if you want. So it's up to you guys.
Okay, alrighty. Thank
right.
you.
Good job. Let me leave y'all alone now.
Okay, so
Hi, everyone.
What do you? Hello.
So do you guys know how to drag the numbers over? Or are you in a place to want to drag numbers over? Or
I put a number in, but you could barely
Oh,
see it.
okay. Yeah. So if you want, you can just drag. If you click on the arrow thing over there, you can just click a
Oh.
number and drag those other ones over. If that works better. Yeah. So it doesn't have
Oh,
to.
okay.
It doesn't have to be the most seeing thing, but it looks like you guys are. Looks like you're doing okay. You guys doing okay? Figuring it out.
Yeah, I think we are okay. Do you have any concern, Guadalupe or Esmeralda?
I don't so far.
Okay. Yeah. Good.
Thank you. Thank you for checking.
All the lines seem to be in the right place, except for when I accidentally moved your triangle. So, but yeah, you're okay.
Yeah.
All right, keep up the good
Okay,
work.
Lupe and Esmeralda, do we have an answer for group number 2? What type is it, or any type?
There we go. Helps when I'm not muted. Welcome back. So, hey, you know, you guys are the first crew that's ever done this on Jamboard ever. So good job. I'm pretty impressed with that. I like how everybody still finds some of the tools interesting and fun to play with. So yeah, it looks like everybody that I've seen, all the numbers are in the right spot and in the right place. So there's not really much I need to go over, other than the fact that when we talk about things a little bit moving forward, you're like, oh, if I say clay or sandy clay or something like that, or if you ever see that in a different class that you're taking, you'll know a little bit about what we're talking about. So good job. This is really much better from a teaching perspective if you have some soil samples that you can bring in and do. So we don't really have that privilege right now the way we're working, but we can, hopefully the homework part of it will bring some of this home. And it's really not homework. It takes 5 minutes to have fun with your family if you would like. So good job. I mean, that blew away my expectations, to be honest with you. So I mean, it would be okay. Now I just got to try to find and put some context to it. What does it all mean? Because it doesn't mean anything if we don't have anything cool yet. Oops, what did I just do? Sorry. I have multiple displays going. There we go. All right. So we classified these. We're good to go. Maybe. Come on. Don't worry about it. So why do we care about soil texture, and why did you take time to classify this? Well, that soil texture really influences the ability to grow plants, and it influences the stability of slopes, which we're going to be talking about at the end of class too. But if you have sandy and rocky soils, water just drains on them quick. So if you have to irrigate stuff over in Turlock and you have sandier soils, you're going to need more water because not all of it stays where the roots are, versus if you have like clay and silt or something like that, it can get compacted. And somebody asked earlier, what happens if all the water gets, or the air gets pushed out, becomes like rock? Well, that's what hard pan is with clay, and it can even prevent roots from growing in there. So clay in the right mix is good, but if you have all clay, it's probably not the best. And one of the other weird things about clay is when you have water in clay minerals, it can expand and contract, and we'll talk about that with groundwater later on. But it also influences what we call the porosity, or the ability for water to move through things. So one of my Twitter friends who teaches geology in Louisiana, he made these really cool UV glow in the dark with simulated like sand and gravel, with the water has a fluorescent dye to it under black light. So watch how quickly the water moves through the black or the sandy type stuff here. So give it a second, it should be playing. There's no sound on it. Or I guess there's a little bit of sound. So these are actually like glass beads that are in there that are about the size of sand and little gravel bits. All right, and compare that then to something that simulates like silt and clay. I guess I could have played both of them at the same time. So what do y'all notice about the differences here?
So there's more loose particles on the one on the right, on the left, I mean?
Yeah, there. So can you expand on what you mean by loose particles?
I feel like it's more like gravel or either air.
Okay. So there's, so do you think there's like more spaces in between the
Yeah,
different?
more space.
Okay. And so in this, we'll call that porosity moving forward. So it's like how much pore space there is, like a sponge has pores for sure. What do you guys notice about the rates at which this is moving through the water?
Well, it's faster on the left compared to the clay one.
Heck yeah.
It takes longer.
Yeah, it takes a lot longer. And sometimes it'll retain that moisture a little bit better on the right-hand side, the silty clay simulant one. So once the water actually gets in, even though it's slow, it'll stay in there longer, versus the other stuff will just drain out of the gravel. So it's important to know if you have a sandy soil or a clay or a silty or loamy one. Good examples are out in the desert. It's hard to find. You have to have specially adapted plants if you have deserty areas or sandy soils that don't get much water. That's where your succulents grow. That's why they like sandy soils, because they have their own water retention devices there. And so one of the things I might have you take a look at, I'm not 100% sure if I will or not, with the homework part, is this soil web. So what's pretty amazing here is the UC Davis has this entire website. Oh, doggone it. I'm just going to zoom out. There it is. Okay. So I think it's zoomed into Turlock here. Yep, we're in Turlock. That's not exactly where I'm living, but whatever. And if I zoom out of Turlock, you can see all these little yellow funny lines on there. And if you click on any one of these lines, it will tell you the name. This is called the Hanford Sandy Loam. Or if I click over here, it's called the Delhi Sand. And you can click on it and it'll tell you exactly the percentages of the soils of anywhere. If I zoom out here, anywhere within the entire United States, you can go in and see what type of soil is in that area. And this is meant for farmers and things like that. But what's kind of cool is you notice we have like 9 or 10 different soils in Turlock alone. You know, back when I taught things like similar things in high school at a lower level, you could actually tell and identify where a kid lived based on the type of soil they would bring into class, which is kind of cool. So I might have you take a look at this later on just to compare and see what your results are to where you live. And so if you don't live in Turlock, it'll work anywhere in California, which is pretty cool. And actually, if you go up north, check this out. I don't know if you've been up by like Woodland or places like this. They grow a lot of rice up there. But if you click on any of, well, let's see here. Willow's clay, so it's much more clay rich up there. And the reason you can grow clay in that, or grow rice in that clay, is the clay keeps the water near the surface, and that's what the rice paddies need. So kind of interesting that these soils have such a huge impact on our life, and we just walk right over it every day and don't give it much thought. So hopefully you'll see that soil texture is a little interesting anyways.
Professor, I have a question.
Oh yes, I can answer a question.
So Professor, this site answers according to the map, and we navigate ourselves, or we can put in a zip code and look it up.
Yes, either way. So let me show you here. That's a good question. So if I hit close, there's a couple ways to find yourself. You can zoom to location. And if you click on zoom to location, you can like use the GPS on your device and it'll do it, or you can enter a zip code or your own location in this little box over there. So it's in the menu in the top left-hand side. You click zoom on location. And if you don't want to do that, you can click on the little bullseye, and the bullseye will try to locate where you are based on your internet, Wi-Fi, and all that other kind of good stuff. So
Thank you.
Does that help?
Yes, definitely. So,
okay.
And are there resources where we can take our sample to a government office or somewhere where they will test the soil for us?
I do not think so. You won't need one. By the end of tonight, you'll be able to take it and test it and know exactly what it is pretty easily. So, but there are some soil labs where if you wanted to do be a soil scientist, you can totally take that and get down to the nitty gritty and figure out like the microbes and all the other stuff that's in there too. But my best friend's sister is a PhD soil scientist, but she works mostly in the forest, so I'd have to ask her. But I could find something for you, for sure.
So Professor, we moved into the country living, and over here it's mostly the soil is like a clay soil, and so water retention is high. So I noticed the trees are not growing as fast. So I brought in some sand to mix in to make it porous. But I wanted to know how much potassium is there, what are the minerals in there, if I need to put in some iron in there. So I want to get some tests done.
I will look into it for you, and I will find something for you. How's that?
Thank you.
All right, no problem. Yeah. So I just want to show you that soil that we do have here. So if you live in clay, that's interesting because there's not too much in Turlock. So you probably live closer to a river or something like that than I do. But in our Central Valley, right, the soil facts that we have here, we have 250 different crops that are grown. And these are numbers from, I think, 2017, but it produces about $17 billion a year in terms of the crops that are grown in the Central Valley. So 75% of the irrigated land in California is here in the Central Valley, and it makes up 17% of all the irrigated land in the entire United States, which is kind of cool. But then the other thing is using fewer than 1% of all the land total in the United States, the US farmland, not just land, but farmland, the Central Valley supplies 8% of the US agricultural output. So 1% of the land is producing 8% of our nation's agricultural output by value here. So it produces a quarter of the nation's food. Isn't that crazy? A quarter of the nation's food, 40% of the fruits and nuts and other table foods and things like that. So this soil is very important to us and to a lot of folks here. So here's what we're going to do. I'm going to show you a few things of what influences soil, the formation of soil, and then we'll take a quick little break, like 5 or 6 minutes, and then we'll come back. We'll look at mass movements. You guys will go on a good virtual field trip where it's not me talking, it's you getting to experience some really cool things and making some observations. So how do you get clay or sandy loam or other things like that? How does that mix of the texture come to be? Well, it's based on a few different things. And the first one is the parent material. So it's the source of the mineral matter. It depends on what types of rocks was the soil born out of, were those minerals born out of. And for us in the Central Valley here, we have a lot of sandy soils because it's the granites that have been breaking down from the Sierras and washed out to where we are here. So if you live in a place that's much older than the Sierras and those minerals have had time to break down into clay, you'd have much more clay-rich material. So this is kind of interesting. The San Joaquin River, if you're not familiar, I should have used a different color here, but it's this brown line on the left-hand side. The San Joaquin River is what the Tuolumne River, the Stanislaus River, Merced River all flow into. But on the east side of the San Joaquin River in the Central Valley, all of the sediments that we farm on and live in Turlock and stuff, those came from the Sierra Nevadas. That's pretty much everything on the east side of the San Joaquin River. Now, that came from weathered granite. It came from weathered volcanics. And so because of that, we have very fertile clays, silts, and sands. For us, it's a pretty big benefit for agriculture. These are some of the best soils in the entire world, but they do drain a little bit quickly. And if you don't have water, that can be an issue. So then if you move over to the west side of the valley, the origins of the sediments on the west side of the valley come from the Coast Range. And I don't know if you can tell here, but these sediments, and that's Gary Hayes, he's a professor at MJC, and I think he adjuncts at Stan State as well. But this is over by San Luis Reservoir, going over to Gilroy and things like that, if you're familiar. But you notice these rocks are all at an angle. They've been tilted up. These are the Coast Range bending up the very bottom of what we call the Great Valley sequence. It's all old marine sediment. So the Coast Ranges on the western part of California are all made of material that used to be once near the bottom of an ocean floor that have now been faulted and lifted and raised out of the water. And this is San Luis Reservoir, what it looks like today. But because it used to come from the ocean type sediments, all of the stuff on the west side of the San Joaquin River, the sediments on the west side of the river, they originate from the Coast Range. And because they come from the ocean, they're very salty, and they have other like selenium and other minerals that get in there that can be a big problem for agriculture. So they're okay to farm. They're not the best. But the thing is, and I don't know why everything's coming out blurry. I apologize. But basically, when you put a lot of water on soils that have dissolved salts and things like that in it, the water will eventually move. And as the trees draw water up to the surface, it brings the salty water up. And as the water evaporates, it leaves the salts behind, and over time makes the soil saltier and saltier and saltier, which makes it hard to grow trees without doing a lot of remediations. So that's called salinization, when too much salt gets in the soil. And it's a problem. So we'll get into more of that with a little bit later on. So I'm going to take a 6-minute break. Go stretch your legs. This will be the last one. Take a break from me talking at you all this time. I promise the next stuff gets really good. And we'll be back in like 6 minutes and we'll go from there. So that's what, 5:50, and maybe might even get done a little bit early again tonight. Okay, so 6 minutes. I'll see you back in just a moment. All right, I'm back. Give me about 2 seconds here, and I just want to show you really quick the awesome the earthquake in Alaska from the other day here, as it appeared on my. Oops. As it appeared on mine. Oh. Where'd you go? Well, no. I'll show it to you later. I can find it and move on later, but I will show you this really fast. So this is where the epicenter was, right outside of Alaska, on a subduction zone, but it still made a strike slip fault, which was kind of interesting. And you can see the shaking intensity map that we talked about last week over there. And luckily, there's not too many people that live in this neck of the woods, so everybody evacuated and was fine. Okay, so now what are we gonna do? Let me show you, and welcome back. I hope it was a pleasant 6 minutes. So we're gonna finish really quickly talking about the other ways that soil can form. This should only take a few moments or so, and then we'll go into looking at mass movements and landslides, and I think it's gonna be pretty cool. I think you'll enjoy it. So soil formation, we talked about the parent material is one thing that affects the soil. The second thing that affects soil formation is the time. So the longer a soil has been forming, the thicker it'll be. It just kind of makes sense, right? Things will pile up over time. So if it's an older soil, it'll generally be thicker. Climate has really the greatest effect on soil formation. So if you live in a hot and wet climate, you're going to get lots and lots of fast soil growth. Organisms are going to break things down. More leaf litter will come on top. The downside is if you live in a really wet and humid environment, it can also wash those soils away. So if you don't have the rainforest replenishing that with organic matter all the time, the soil is just going to wash away. And after a few years, you're not going to have very rich soil at all, which is happening in like Brazil and places like that. So dry and cold climates, it's really hard for soils to form up there. You don't get as much organic matter. Things don't break down as easily, either through mechanical or through chemical weathering. So it's just a slower soil growth. And then if you have lots of organisms really are the main source of the organic matter that get into the soil and can build it up. So just like we compost and I don't know about we, but my family composts, and maybe you buy compost to put in your garden if you happen to garden, you're just putting in organic nutrients, things that are dead. When I say organic, carbon-based life forms that have died that you put in there to make your soils good. And so the microorganisms in there, like bacteria and fungus, they can decompose those plants and animals, and they turn them into nutrients into the soil. And one of the big parts that everybody overlooks, and it's not like super important for you to necessarily know this other than for the class, but the nitrogen cycle is super important because there's only a few certain bacteria in our soil in the whole entire world that can take the nitrogen from the atmosphere and the nitrogen from decomposing organisms and turn it into the nitrogen that plants need in their roots to grow. And if we didn't have that, nothing could grow. So it's really important that these little bacteria that you see in the bottom right here, they stay around forever and forever, and we give them what they need so that they can continue to fix nitrogen in the soil. But if these little bacteria didn't exist, plants couldn't exist. And if plants couldn't exist, you know, the rest of the things that consume the plants and rely on that couldn't exist. So just kind of an interesting tidbit here that's in your soil that's super important. And then also the slope influences the soil formation. If you have a really steep slope, things are going to slide off and you're not going to build up a soil. It's always going to wash off into a flatter place. So steep slopes, soil washes off. Flat slopes, everything builds up and will pile up over time. So the right-hand picture over there, this is Death Valley. And you can notice It's 11,000 foot tall mountains that then go down into the valley there, and everything that washes off the mountains just piles up. And that's basically what's happened in our Central Valley as well. All the stuff that's washed off is piled up and left in our flat area here. So now, here's your at-home activity for tonight, or not tonight, but whenever you want in the next week or so. But basically what I would like you to do is sample some soil near your house. Ideally, it doesn't come from a garden. We want to get a natural feel of what that soil is. And most people's gardens have had amendments put into the soil. So you may have to scrape a small little hole, but all you want is just a small little amount of dirt. So maybe like 2 teaspoons, 3 teaspoons, a couple of spoonfuls, all right? It's just like Mary Poppins says, a spoonful of dirt will make your day go good. I don't know if she actually said that, but she should have. So basically what you're gonna do then is there is this soil texture chart, and I think I might have to put this link in Canvas, but basically what it is you follow the instructions on the chart. So it says start, place approximately 2 teaspoons in your palm, add a few drops of water and knead it. So the knead it means to rub, like bread or something like that, dough. Knead the soil to break down the aggregates. So if there's clumps of things stuck together, the water will be on there and you just knead it down and break it till it's all smooth. So then it says soil is at proper consistency when it feels kind of plasticky and moldable like moist putty. And then you just answer the next question. So you follow the arrow. It says, does the soil remain in a ball when squeezed? If it doesn't, you follow those. If it does, you just follow down the chart. So it's a yes or no question where you're just following them. And at the end of it, it'll tell you if it's sand, loamy sand, or some of the other types of soil based on what you've done to it. And this is how a lot of the farmers, they can tell what type of soil they have just by rubbing it and pinching it in their hands, and they don't need to send it to a lab or sift it or sieve it or anything like that, which is kind of a cool thing. You know, when you work with land long enough, you get a sense for what's there. So if you have kids, this would be a fun activity to do with kids. If you don't have kids, it's a fun activity to do on your own. You get a little dirty. It's a good exfoliant, so your hands will be nice and smooth and soft afterwards, which is kind of fun. So then just in your notes, your sketch notes, you're just going to record your findings like, oh, what type of soil was it? And then you can head on over to that soil web app and click on that and see if the soil type in the soil web app matches what it says for your house. And it, you know, usually it's fairly close. You know, if it's different, then we can figure out why it might be different. Things have changed over time, right? Construction and things like that. But it's kind of a cool deal. So I'm excited for you to do that. Maybe I'm just a nerd, but I think it'll be kind of fun. If you want to take pictures, feel free to take pictures and add that into your notes as well. If you just want to draw it, that's fine. Some people just smear the dirt onto their papers and take a picture of it, whatever you want to do. All right. So that brings me now to our mass movement virtual exploration here. So we're going to get back into our breakout groups again. And in our breakout groups, you're going to watch some of these mass movement videos on this Google virtual tour. So let me get this link and send that out to everybody here. I do have a question. And I guess the question is everybody okay with a few S-bombs in a video? Because there's one video where a guy kind of loses his marbles saying the S-bomb because he just witnessed a really massive rock slide. Everybody's fine and nobody's hurt, but are you guys okay with S-bombs? I can find an alternative video if you don't like that. Anybody offended? I'll take that as a no.
Okay.
Are you guys okay with that?
Yes, Professor. That'll be fine.
Okay. All right. So I just want to make sure. So I will say if you have kids in the house or something like that, you might not want to just play the sound with them around. Okay. So I forgot to give you the link. There we go. So I think this link should open. And what it'll do is when you click on it, it'll open up a page that looks just like this. It's kind of the starting bit of sorry, I can't think and talk at the same time. It'll give you the starting page for the Google Earth tour. So it says table of contents down in the top bottom left. It's very similar to the plate tectonics thing we did earlier, but it's for mass movements. And it's starting out on a picture from La Conchita in Southern California. And we'll see more about them a little bit later on. But if you click the arrow buttons down on the bottom left-hand side, it'll take you to the next stop. And if you don't want to go to use the arrows, you can click on the table of continents. Table of contents. If you want to do table of continents, that's more plate tectonics. But basically what happens here is it'll take you into the area into Google Earth. And if you want to close a table of contents, you can do that. By left clicking on your mouse, remember it drags Google Earth around to the left and to the right. If you have a wheel button on your mouse, you can click down on the wheel button and move it around, and it kind of rotates everything. If you use your wheel button to zoom in or to zoom out, you kind of roll in to zoom in or zoom out. If you are on a laptop, if you click the shift button, hold down the shift button and then click down a left click, it'll move things around for you like that as well. So you can kind of get an idea of what's going on. So this first place here is in India. And what happens is at each stop in the top right-hand corner, there will be a little video clip for you to play. So I'll play this one together for everybody, and then I'll let everybody experience the rest of it on their own. So you can click on this. Right, that'd be a little scary. And so this is kind of the approximate location in this area of where that happened. I didn't get a solid GPS on there, but underneath the video, there'll be a little explanation of where the little mass movement happened. So in your group, what I'm asking y'all to do is, if I find the right Jamboard, so let me put on the Jamboard here, copy link, chat. Sorry, I'm talking to myself. And hopefully, let me know if I might need to change the permissions on this one too, don't I? Yep. All right, hold on. Gosh, dang it. Anyone with the link is an editor. All right, so the Jamboard link, there it is. It should open you up into this. And so when you get into your groups, basically what I'm going to ask you to do is just fly into the various stops in the virtual tour, watch the video clips. On some of them, on some of them, if you see little arrows on the right-hand side, there's the video. But then if you click next, it'll show you, there's some pictures that are in there as well. And it'll kind of tell you where you're at. So some of them will fly in and you can look around. If you get stuck in a photosphere like this, you can look around, you can zoom out. If you don't want to be in that photosphere and you want to see the Google Earth version, you click on the arrow on the top left-hand side over here, and that'll get you out a little bit. And then you can kind of use those keys in Google Earth to zoom around and see what's happening. And what's kind of really funny at this site, for some reason, Google Earth really messed up and it made a lake. It looks like Event Horizon, right? A black hole's in there or something. And look at all the metamorphic rocks. No, but I don't know why that's there. It's just a Google Earth error. If you travel there, you will not see that in real life. And if you happen to get out of it and you see this funny looking thing over here, just click present and that'll get you back into your mode again, where you can go around and see all these different things from around the world. All right, so in your group, what you're going to be looking for then is watch the videos. What do you notice? So put your notices in yellow. What do you wonder? You can put that in pink. And then what do they have in common? So what are some of the things that you're noticing that they have in common? And that's what we're going to be looking at. I'm going to give you like 25 minutes here, maybe 20. Yeah, we'll start at 25 and see if that's good enough. And in those 25 minutes, take a look at some of those videos, respond with each other in your groups. If you want, you can have one person share the screen for everybody else, or if you want to watch them individually, like, okay, everybody watch this video. It's up to you guys on how you want to do it. But I think you'll enjoy it. All right. And these are mostly fairly new ones as well. So I'll give you 25 minutes. I'll stick you in your breakout rooms right now. Does anybody have any questions before I get going or before I send you out? All right. I must be the best explainer in the entire world. You guys can tell my wife that. I don't think she believes I'm the good explainer. But all right, let's see here. I'll give you 25 minutes for this. And if we get done a little early, that's totally fine. But I want you to have fun. Well, not fun. Most of these here, or all of these, are non-lethal versions. All right, so nobody died in any of these. That's the good news. 25 minutes. Here we go. And open all rooms. And so while everybody else is doing that, I'll play a few little video clips here for the folks that haven't gotten the access to the resources here.
Holy shit! We would have died. If we were coming down, we would have been dead. Holy shit! Holy shit! Dude, the rock is Smoothie's gone at the top! Smoothie's gone! Smoothie came down! Smoothie is gone!
So as you can tell, that was very bad. Here's the before, here's the after. That's old Smoothie that fell off of the rock there. That was the rock fall that you just witnessed. So that was in Idaho. This next one is back again in India. I don't know that I'd be standing so close to it right after a rock fall, but now down to South America and Ecuador, the Rio Coca.
Estamos viendo el pensamiento de Río al poco. Todo. El marketing. Está en el rumbo tenaz. La montaña se viene abajo. Todas las 150 o 100 kilómetros. Vamos a buscar el todo. Realmente cómo están los derrumbos. Hay escala y amigos viendo el derrumbo grande. Posible etapa del río Coca. pensamiento que se puede dar. Sí, está cayendo más. Ya lleva media hora. Está prácticamente represarse el río Copera. Vamos a ver la magnitud del rumbo, ¿ves? Se ve toda la montaña abajo. Toda la montaña, simplemente. Estamos ya. Está tapado.
So very much different reaction, right? Very calm and quiet. And here's kind of the aftermath, and it blocked the river. So that's why that picture is there. And then that can be bad sometimes because it blocks the river and then everything can flow out from underneath it. Right, so this one's in China. You can see the aftermath in that area right here. Crazy, huh? All right, I need to stop and I'll come back to this a little bit later, I think. And we're gonna go bounce around in the breakout rooms here.
Professor.
Hi guys, sorry, I was bouncing around here, forgot where I ended up. Are they working for you? You guys seeing some of them?
Well, me, I'm just having problem with the Wi-Fi, but I know how to work it out. It's just the
Oh,
Wi-Fi right now.
okay. Yeah, so I guess once that comes back on, um, I have other videos to show and stuff too. So if this doesn't quite work, but just, yeah, start adding some notices and wonders and if you can, or have maybe somebody share a screen, maybe if that works too. I don't know. So,
Sounds good. Thank you.
all right. All right, so where were we here? The China landslide, we saw that. Ooh, now the Snake River in Wyoming, near Grand Teton National Park. Yep. So you can look around here and you can see the old scar right into this neck of the woods right here. So this is kind of an interesting little time lapse, isn't it? A bit different than what we saw previously. So you can see it's not moving very quickly at all. It's kind of this creeping, slow motion landslide, but still very damaging. And that was the aftermath right there. Notice the nice big sedimentary beds in the background. All right, where are we off to next? Ooh, Norway. So here we go. Pretty impressive, huh? That's what we call a quick clay landslide. We'll talk more about that as a full class. But a little closer to home, we have the Ferguson rock slide that happened back in 2006. Right along the Merced River Canyon here. It's on the way to Yosemite. If you've ever been there in the last 15 years, you've had to go around a detour. And this is the rock slide area. And here's what it looked like. Oh, you know what? I should tell everybody they don't have to watch all of that. So now we're going to Montecito down in Southern California. What's kind of interesting here is you can kind of see the before and the after and the fire that happened there.
It was a million miles an hour in slow motion. That makes sense. Survival gear, survival mode. Wake that
That car is being carried away, not driving, by the way. So if you zoom in on Google Earth here, you can see there's a kind of a brownish, blackish char everywhere. That's because a lot of the plants and everything were burned quite severely in the last fire they had there, the Thomas fire. You can see it really big here. So when the rains came, it just flushed everything out of the mountains right down Montecito. And so what you're looking at here, there's no video. I should tell that to everybody too. All right, hi everybody. So I've seen a lot of good notices and wonders. So what I'd like to do just really quickly is kind of go around for the groups. I'll leave your boards up here to share with everybody else. But what are some of the, you can either just tell me one thing you noticed, one thing you wondered. Let's see, somebody has a question, I think. Yes, that was, well, it was 24 and a half minutes. So, but the thing is, the links are here, so you can go back and rewatch them all that you want. I just want to make sure we're out of here by 7 o'clock. So, yeah, we're good to go. So I guess, first of all, just before we move on, did you guys enjoy being able to look at that on your own, or would you have preferred I just showed everybody where they were and like guide it myself? What are your reactions to that?
It was fun on our own.
Okay, good. So, and somebody says, okay, good. So there were landslides. Some of them were in developing countries for sure, but you know, I there were some in Norway, there were some in the U.S. So I tried to get a lot of decent ones in there. And this has been one of the major good things about cell phone cameras and stuff as well, right? Is that they're so prevalent now. There's just so many more videos of things that, you know, 15 years ago, this would have been unthinkable to have all these videos. It was hard to find one or two or something. So this is really cool. All right, so how about group number one? Would somebody care to share just really quickly here, like one takeaway or one thing that you noticed they had in common, something like that, just like really quick, 30 seconds or so.
So wait, like about a specific one we saw, or
Yeah, whatever you would like. Yeah, your big takeaway, something you noticed. Yeah.
I wondered, well, my partner, the one that was in my group, she had a good point. Because a couple of the videos we saw, they all had some sort of similar weather, like raining in a couple of videos, it was raining.
Okay.
And so she was wondering, like, if rain is a part of the cause of how the landslide originally, starts. And
Right.
yeah, so could the weather be a matter of, whether or not it's, yeah, you know what I mean?
Yeah. Is weather a factor, whether or not?
Yes.
All right. Yeah, totally. All right. Good observation. Thank you. All right. So group number two, you got some ideas you'd like to share? Or one idea, please?
In our group, we kind of like separated like which slides we did. So on one of them, on slide 5, I noticed that the dirt that was sliding down from the mountainside was darker than the dirt on the mountain. So the mountain was like a lighter color, and then the dirt that was coming off the top was darker. So I was wondering why it was darker than the rest of the mountain.
Interesting. So that was, the Rio Coco one?
Yeah.
Okay. And it's kind of interesting. That's a good question. So we'll look into that. And weren't the two ways that the person in this video approached it versus the person in the Idaho old smoothie?
Yeah. I thought those guys in that video were frat boys, because I was listening to them. I was like, they sound like frat boys, kind of.
Yeah, rock climbing culture.
Yeah, it was funny.
Old smoothies gone.
Oh my god.
Old smoothie. Yeah, it got its name because it was just a big smooth rock spire that all the rock climbers used to climb. So that's how it got its name.
Okay, we didn't know who Smoothie was for a moment. I was like, what? Smoothie?
Yeah, it wasn't a person, it was the rock. So if you looked at the thing, you could kind of see the before and the after of what moved down. But all right, thank you. So how about group number 3? Quickly here, what'd you see?
Something that we noticed was how the movement happens so quickly. Like at the beginning, it'll start slowly. Like for most of these, they'll start super slow, but then they happen pretty fast.
All right. So like there were precursors, like you could tell something was going to happen that was because of small things. All right. Interesting.
And for the wonders, we also wondered, some people were a lot more calm than others in some of the videos. So we were thinking, we were wondering, are they used to things happening like this?
That is a great question. Interesting, something to look into. All right, thank you. How about group 4? Anybody from group 4 like to share really quick?
I would like to share. So
Okay.
the under we noticed that all of these were like hilly areas where the landslide was happening. And the type of mud that was sliding down was similar to the first one that we saw from India, that it was just dry. And the other one where it was raining was the Malad, India. It seemed as if similar type of mud, but only wet because of rain.
So similar like soil types and stuff, but maybe the
Yes.
water is different. All right, thank you.
Yeah.
And the hills, that was an interesting observation as well. So group number 5, would you like to share something really fast? Or are you guys happy old smoothie is gone?
So, for I think it was video number 4 for Rio Coca. Yeah, I noticed that the men were like, I guess like okay with recording, like they were not scared. Like I would not be able to be recording seeing that close. Like I thought it was close.
Yeah,
how the guy was recording.
I wouldn't want to stand there for certain. And I don't know if you guys got a chance to see in that slide, but this is what happened afterwards. And you can see the cars parked. That's probably about the same place where they were parked where they made the video. That's crazy. But it went
and I also, sorry.
Oh yeah, go ahead, Annalise. Sorry, I didn't mean to cut you off.
I noticed like each mudslide, like each color was different of the mud. So I'm not sure like if the dirt like it has like different minerals or if they weight around the same, or if it's like more clay than the other ones are like more sand or
Right. Interesting idea. And I just want to, I'll just going to zoom out really quickly here and put it northwards. So we're just on the back side of the Andes volcano. So all of this stuff, and there's another volcano right here, everything that we're seeing in this river is basically old volcanic sediments and ash and things like that. But I want you to notice what happened after it slid across. It dammed up the river, and basically it dammed up the river of unstable sediment, and it makes a lake behind it. And until that lake and the water finally fills up and goes over the top, it can be bad, especially if it spills over the top and everything, you know, just floods the area. So thank you. Those are really good observations too. Not that anybody has bad observations. Group number 6.
One of the things that we thought, or we thought was interesting is some of the landslides, they didn't come down from a mountain. They actually, the earth just moved either forward or backward. And the one where, I don't remember where it is, where the houses went into the ocean.
Oh yeah, Norway, yeah.
Norway, yeah. And then the other one too, it looked like the earth was cut in half and half was moving forward and the other one was just staying put.
Interesting. All right, thank you. Yeah, when the Norway film came out, or that was just this summer, I mean, a lot of geologists lost their mind because that was pretty crazy one to see. How about number 7? In group number 7, sorry. They're like, not me, you, me, new.
Well, we noticed that some of them happened, some of the landslides happened like really quickly, like out of nowhere, while the other ones like just took a while and they just kept going slowly, kind of thing.
All right, awesome. All right, thank you. And then some good observations. And then number 8, last but not least. It can be a notice, it can be a wonder, or whatever.
So I forgot what slide it was, but I remember it was like the snake one, the snake landslide.
Okay.
And it was like there was like a man walking across it, so it must have been going slow enough for him to walk across it. So I was just wondering like how, like what determines how fast or slow it goes.
Ooh, that is a good question. So, oops, let me go back to Snake River here. I'll just show you. I I think that's next. Nope, China, sorry. Snake River, yeah. And so the Snake River landslide, that happened right outside of Jackson Hole, Wyoming, also near the Grand Tetons. Oh my gosh. Come on, Google Earth, fly. There we go. But you know, the one thing I wanted y'all to see too is that slide was in 2011, and these Google Earth images are from, you know, not too far ago, maybe a year or two ago, but you can see the remnants of the landslide going out into the Snake River here. And it definitely caused a lot of damage on the highway. You couldn't drive across it. And if you see over on the left-hand side, you can totally see the sedimentary rocks. We're dancing. All right. So anyways, thank you for the observation. Very good observation. There we go. We're good now. Let's see here. So thank you very much. And then the last thing I wanted to show you, there were no, well, the debris flow in Montecito and Santa Barbara was pretty crazy. And that one was because of all the fires that had happened the year before. But in Del Porto Canyon, just outside of Patterson here, what I outlined were the remnants of two big landslides that are in Del Porto Canyon. And what's kind of interesting is if I zoom out just a little bit here, and I kind of do like this, you can start seeing the curved nature of the rocks that are there. And it's basically, if you think of the Central Valley sediments as flat layers, at the edge of the Central Valley, right over here by Del Porto Canyon, as the coast range started coming up like that, maybe I should go from the other side so it matches. As it started going up like this, I don't know which side, basically the sediments got upturned, and that's what you're seeing are kind of like the pages of those upturned sediments lying around right here. So this is all sedimentary rock. And the reason I highlight this is because just yesterday, the Del Porto Water District approved a dam to go right across the canyon right here. And they want to put in an 80,000 acre foot reservoir that will go all the way back and fill in most of these canyons right here. But there are, I think, at least 7 different known landslides that have happened right here. And it's about 10 miles or less than 10 miles away from a major fault. So the geologists around here are having some issues. And, you know, the environmentalists, me included, are having some questions and concerns that this actually got through and got passed. So I just wanted to make you guys aware of that. So great job with those notices and wonders. So let's try and put this all together in the last 20 minutes or so here and help you understand what this all means. We're going to skip over a little video that I have. I'll put it in Canvas if you guys want to watch the little video on rock falls in Yosemite. But what you're looking at here is a map of Yosemite Valley, and the colors show the different angles of the slope. So if it's blue, it's a pretty flat area, and the more red it is, means it's a really steep slope. So from like 51 to 90 degrees, so there's 90, this would be about 50. So that's pretty steep. And as it goes down, it just means it's less and less steep. So do you think steep slopes might play a role in rock falls in Yosemite? Maybe. The answer should be yeah. If you haven't been to Yosemite Valley in a while, go there and we'll see some different things. So my next thing I just want to show you here really fast is the rock falls in Yosemite. There's not any particular season that they tend to happen in more frequently than the others. It seems like the biggest ones so far, so the size of them, the biggest ones generally tend to happen in the winter time based on what we know. But there are equal amounts of rock falls in the fall and in the summer and in the spring. And some of it can be from frost wedging. Some of it can be from earthquakes. Some of it could be from just the rocks falling apart. And that little video clip that is right here talks about all the rock falls in Yosemite. It's a great video. Greg Stock, the park geologist, is in it. And he actually takes LiDAR and scans all of the valleys. And so whenever there's a rock fall, he can go back out and scan it and tell you exactly how much rock has fallen. And there's generally a decent sized rock fall at least once a year in Yosemite. So you got to be smart and safe about it. And the other thing too is if you want to find all these landslides, if you all of a sudden find yourself to be a fan of landslides, the landslide blog run by Dave Peltley, he's from England, but just an amazing geologist and researcher on hazards and landslides. And so he's the one that basically keeps all the landslides that he finds on his website. So that brings us to mass movements then. And let me show you, what do all these things have in common that you guys have all pretty much nailed on the head already, but we're just going to kind of formalize it right now. So what is a mass movement? It's just the transfer of rock or soil downslope due to gravity. So landslides, rock slides, rock falls, creep, slump, things like that. They're all types of mass movements, but the names specifically call out the way they move, okay? And what you're looking at over on the right, I can't remember who went to Utah last week, but somebody was on their way to Utah, and over in the copper mines, they had one of the biggest landslides known in the history of mankind, and it happened in a tailings pile from a big hole in the ground they had dug out to mine the copper underneath, and the whole entire mountain just basically filled in a big chunk of the hole. So that's what that video is. So there are several different triggers of landslides, which you guys mentioned. And so triggers are the things that make it happen or make it go. And water is 100% like one of the major triggers for a landslide. And so it can be for a couple of reasons. The first one is that it is water. If you gently water a slope, it's good for soil cohesion. So if you think about sand at a beach and you put a little bit of water in it and you want to build a sand castle, the sand sticks together with the cohesion of the water. But if you put too much water in there, the water spreads the molecules of sand apart, or the sand bits apart, and it becomes unstable, like we saw with liquefaction last week. So a little water is good, too much is bad. And if you put too much in it, it overcomes the cohesion and it lubricates the soils and the rocks, and it can make it start sliding down if you have enough of a slope. And don't forget, water, 1 gallon of water weighs 8 pounds. So if you're putting millions of gallons of water from rain on a soil, that makes it even heavier, which gives it even more mass to maybe break rocks and things and let it slide down. So that's what you're seeing here. This is the Oso landslide on the left that you see here in Washington, and it went into a neighborhood and buried quite a few people. It was a pretty big tragedy that happened about 5 or 6 years ago. Okay, so water is one. Oversteepened slopes, that means you have slopes that are too steep. So rocks and sand are most stable at about 25 to 40 degree angles. That's why I have the pyramids over here. The ancient Egyptians knew that, and that's why they built their pyramids at those specific angles, because they knew that's a stable slope. And that's why they're still here, what, 3,000 or 4,000 years later. But if you go any more than that, gravity will want to take over, and eventually, like the coasts over here in San Francisco on the left, those will eventually fall into the ocean and gravity will take over. So oversteepened slopes are another trigger. And then the big one for California is the removal of vegetation. So if you have a fire and it burns all the trees, or if you happen to maybe you bulldoze all the trees out for a farm or something, those trees and those plants and the roots hold together the soil particles. And if you take them away, all of a sudden, the rain is just going to wash over, and there's nothing going to be slowing the rain down. The rain can move faster. It can soak into the ground easier sometimes and take everything with it. So it's really, this is a big deal in California after wildfires. And this was a picture after the Rim Fire, which was one of the largest wildfires in California history up until 4 or 5 years ago or so. And this is on the way on the Tuolumne River. And also what's really crazy too is when plants burn in high heat, they release a lot of wax. And so in these freshly burned areas, they also get a coat of wax that goes on the soil, which in some areas makes it hard for the water to get in. And the water just falls right off and takes all the debris with it, and can create those debris flows. Earthquakes can trigger rock falls, just like we saw. The old smoothie video you guys saw was a magnitude 4.5 earthquake a little bit nearby, and it shook the rocks off. And after the Lone Pine earthquake in the 1870s, John Muir was in Yosemite and said after that earthquake, just rock falls were falling all over the place. So that's a big one. And then, oh, the reason I have this bag of cereal here is the sediment kind of settles after it gets shaken, just like you see right there, the liquefaction. So what I'm going to be asking you to do in your little sketch notes is I'm going to show you these rock falls. I'm going to show you some videos here. All I would like you to do, it says stick figure sketch. You'll see that. Just draw a little stick figure that kind of is next to something that demonstrates what a rock fall is. And so in this case, rock falls literally fall through the air. What you saw in Idaho was a rock fall. What we see in Yosemite, like over by Curry Village, those are rock falls. They fall freely through the air. And the stuff that looked like smoke, some people were mentioning in their notices and wonders, that wasn't smoke, it was pulverized rock. So as the rock fell down and broke and pulverized, it just turned into dust. And so here's one other video I wanted to show you just really quickly here. This is from Switzerland. And if you want to see a rock fall, this is the place to see a rock fall. So, pretty impressive, right? I wouldn't want to be down. I wouldn't want to be downhill of that at all. But can you imagine being right next to the side of the hill? This guy didn't scream old smoothie was gone, so maybe he wasn't too excited. But oh, come on, go. And so the last big rock fall we've had in Yosemite, well, there's been a couple, but there was one in April of 2009 called the Awea Point rock fall. It happened right underneath Half Dome. And a bunch of rocks fell off the cliff and smashed and broke things. Nobody was hurt, luckily, but you can go on YouTube and find all kinds of videos on rock falls in Yosemite. But I was there like 3 days after it happened, and everywhere that looks like dust and smoke and ash, it's actually just the pulverized powder of the rock. And so that's some of it on my finger there. And sure enough, we were there last year with some high school students on a WildLink expedition, and this is what the remnants of the rock fall look like. And you can still see the trees were chopped off at the top from where the rocks came through, and just the boulders smashed the trees. So if you're ever in Yosemite and it sounds like thunder or a jet plane flying over, go get behind a big rock or a big tree, or get to the middle of the valley so that you'll be okay. So rock slides and landslides then. So those are rock falls. The rock slides are where everything literally is in the name. The rocks or the land slides across a fairly flat surface. So it doesn't mean it's not on a flat slope. It just means it's on a flat plane or a flat surface kind of going down. And you saw lots of different landslides and a few little, the debris flow was kind of like almost like a rock slide. So it's relatively dry material that suddenly moves along the flat surface. And it moves like a liquid, so that's where it's kind of weird. So here's another little landslide. This one is from Washington, and you can see the little precursors of the sediment falling. And the reason why it's getting jiggled is all the trains going by this really oversteepened slope of sediments that are fairly loose. And jiggle, 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 jiggle. Give it a second here. There was a geologist out there filming it because they knew something was amiss, but I don't think they thought this was going to happen. So remember, this is kind of very similar to the Rio Coca video that you saw, where little bits go, and then all of a sudden, so yeah, that's a landslide right there. We have another type that's called slump. And so in the Coast Range, we'll see quite a few of these slumps, and it's possible that those landslides I showed you by Del Porto Canyon might actually be a slump. But basically, it's where the rock kind of breaks. And the difference here is there's this curved surface. So the area that it slides on is kind of curved, like a slide at the park or something. So that's what we call a slump. We're just kind of like that. And this is a picture of it over by near Hollister in the Coast Range. You have to see it to experience it. And then I don't know if you've ever driven in the foothills, you've seen fence posts that are kind of leaning over or telephone posts that are kind of leaning over. That's because it's from a type of mass movement called creep. And basically what happens is you have a really thin layer of topsoil on the top, and it slides ever so slowly at, a millimeter or two a year, maybe a few feet a year at the most. But it gently slides downhill. And as it does, the things that are in the soil start tilting with the direction of the flow. So in this case, when you see the fence posts are pointing over like this, the whole hillside is slowly moving in that direction. So that's called creep, when it just slowly creeps along and moves along. And then the last one was a debris flow, which you guys saw the video of in Montecito. So these are very common in California after wildfires. This year, if we get a big rainstorm at all, even though it's supposed to be a La Nina, you can still get heavy rainstorms. What's really impressive and really crazy is we can get these massively huge debris flows. And in Santa Barbara, all those boulders came from 1.5 miles, 2 miles away up in the mountains and were traveling down in these debris flows. That's what can be carried in those debris flows and deposited. So it'll annihilate anything in its path. So we are very near the Coast Range where we had the big fires in July and August, Del Porto Canyon too. So if we get bad storms in California, keep your eyes out in the news for debris flows. They can be slow, but they can also move over 100 miles an hour. And so what you guys saw at that Hobart Junction in the Snake River, that was kind of a combination of a debris flow because everything was really oversaturated, and kind of a very slow landslide. So it was a kind of a combination debris flow landslide that you guys saw on that one. And so that brings me to the last little piece here, which is La Conchita in California. So if we were to look at these topographic lines, which we haven't really done super much in this class, when you see topographic lines that are super close together, it means you have a very steep slope. So you have a very steep slope in La Conchita. And basically, this is what it looks like from the side. And you have that whole little enclave of people that live here. And I see lots of freshly exposed dirt on the side, and you have ag land on top being irrigated. And the result of that was irrigating on top of loose sediments that used to be seafloor sediments that are now mountains that are on a very steep slope. Nothing was really stuck together really well, and this is what happened.
It was a normal day on January 10th, 2005.
Oops, I don't know why there's a kid narrating this, but whatever.
California. Until bam, 400,000 tons of mud started to slide.
Yep, 400,000 tons of mud went down there, and it basically
It was
buried.
a normal day on January.
Quiet, kid. This is in 2005, and it buried a huge amount of the houses that were there. Killed 10 people, 36 houses were destroyed. And this is the thing we need to be cognizant of in California is how could anyone have known that this area was prone to landslides, and why would you build there, right? Well, hopefully you've had a class like this now, and B, hopefully the real estate agents and things said, hey, this is a bad area, because back in 1995, there was a landslide in the exact same area in 1995, and then 10 years later, there was another one. And so these are debris flow pictures from the 95 slides that just, buried houses. So now, if you go there, the last time I was there was 2013, there's a big warning sign that says, hey, you're entering a landslide area. I wouldn't live here. I wouldn't even come in here, enter at your own risk. So that's kind of the end of that. So loosely consolidated over steepened slopes, you generally have a lot of landslides and rock falls. Yosemite is because it's made of granite, it doesn't tend to fall apart too easily, but it does over time. And that's the big deal. So I'm going to skip through this. I'm going to go back to here. So for the big idea, How can weathering and erosion of rock be both beneficial and hazardous for life? So tonight we talked about the mechanical weathering of how we can break those big rocks into small pieces. Through those processes, we talked about how chemicals can dissolve them and move them around. We talked about how it makes soil. And then we talked about how that soil and those rocks can then be moved using mass movement. So that's kind of what your sketch notes should look like. Sketch some different ideas, a lot of different things that are in there. And then for the big idea, just please summarize really quickly. How can rock weathering and erosion be beneficial for life? And how can it be hazardous for life? That's kind of the big things I want you to take away from this. And I think that's it for tonight. So good job. I'm right on the button, 7 o'clock. Let me put in the sunshines and blues here. And then y'all are free to go and have a good Friday night. Let me see here. I gotta get my stinking chat box back open. Woo. And now everybody's going to be talking about smoothies gone. I know that's going to be your weekend. You're just going to be screaming out to all your friends, smoothies gone. Yell at Jamba Juice next time you go to get Jamba Juice. My smoothie's gone. So yeah, that's all I have for tonight. Sunshines and blues, and then you're free to go, or if you need to stick around for questions or whatever, I'm here. But that's it. And have a good night, and I hope you enjoyed some of it. All right, bye guys.